Hello everyone, and welcome to session 71 of the Porous Media Tea Time Talk. We're part of the Interpol Young Academy and aim to bring together early career researchers, PhD students, and postdocs, and give them the opportunity to present their research worldwide through our live StreamYard platform. So I'm Sarah, and I'm joined in the studio today by my friends Chiara and Marcel to chair this session. And today we will have the pleasure to host Maria Iris Lönartz from the University of Bonn and Iman Kivi from the Imperial College London. So please join me in welcoming us and feel free to engage anytime in the discussion, writing your comments in YouTube, chat, or questions. We will have Q&A at the end of each talk, so feel free to engage whenever you have a question. So without further ado, let me introduce our first speaker, Dr. Maria Iris Lönartz. She is a geologist and postdoc at the University of Bonn in Germany, working in the geochemistry and petrology section of the Institute of Geosciences. Her research lies at the interplay between reactive transport processes in porous media, microfluidics, pore-scale modeling, and fluid cell Raman spectroscopy. And our current work extends to studying aqueous corrosion behavior, which is relevant for radioactive waste management. But before that, Mara completed a PhD in geosciences from the Jewish Research Center with a thesis on the effect of porosity clogging on the diffusivity of porous media, which actually will be the topic of our talk today. So Mara, thanks for being with us today, and the floor is yours.
Yeah, thank you, Sarah, very much for this kind introduction and for inviting me to giving a talk today. So, as Sarah already said, today I would like to present you a part of my PhD project, which was focused on the porosity clogging, on the effect of porosity clogging on the effect of diffusivity of porous media, studied by novel microfluidic experiments and pore-scale modeling. So the overall background or motivation of this study was to better understand geochemical processes at the pore scale, which are, for example, very relevant for the final disposal of high-level, so heat-generating waste. And as you might know, several countries are relying on a multi-barrier system, which confines the vitrified waste surrounded by a steel canister, concrete, and a host rock here, for example, clay rock. And especially at the interfaces of these materials, chemical and thermal gradients promote the dissolution and precipitation of mineral phases, which in turn, of course, change our pore geometry and reduce the porosity. And with this, also the transport properties of our porous medium, like the diffusivity and permeability. So in the case of mineral precipitation reactions and coupling the diffusivity and porosity, continuum scale models usually use the so-called Archie's law and predict the case of clogging as a final state, occurring in this example for after 10,000 of years. However, more recent studies have shown that Archie's law is maybe not the best choice to consider porosity clogging. As you can see here in the work from Chamou et al., she conducted counter-diffusion precipitation experiment in a sandy column, precipitating pseudostine here. And as you can see here, Archie's law works pretty well to reproduce the experimental results for a non-reactive system. However, when it comes to precipitation reactions, the effective diffusivity, of course, decreases and was hard to describe by the model simply by adjusting the porosity. Even though she was, for example, significantly decreasing the porosity, it was not working pretty well. And with this, you overestimate, of course, the amount of precipitate. A more recent idea was proposed by Deng et al. She conducted two-dimensional pore scale studies, considering different initial pore geometries and different nucleation and crystal growth scenarios. So for the homogeneous, she observed or she modeled that there was the formation of a pattern here on a precipitation front. And in the case of heterogeneous nucleation, we can see here is a growth on the initial sand. And yeah, so with or based on those trace of experiments, she proposed an extended version of Archie's law, considering a critical effective diffusivity and critical porosity, and adding an additional fitting parameter. However, as you can see that the experiment or the results were still not captured by the model, and the critical effective diffusivity you can see here were simply estimated. And yeah, there was not really an answer on why do we still have like an ongoing diffusive flux or a non-zero diffusivity. So we were asking ourselves, how do we define actually the critical effective diffusivity and critical porosity? What is the physical meaning of A? And are there maybe other key pore scale parameters that need to be considered if we think about the case of clogging? For this, I designed a lab-on-a-chip approach. So you have a PDMS glass chip, and on the left side, 2 reactants were injected of the same concentrations, going through those channels here, the supply channels, and on the right side, there's the outflow, and those channels had a height of 10 micrometers and were connected via a porous reaction chamber, just 1 micrometer height. And the idea was here to generate a constant high flow rate so that we have a constant concentration and triggering the precipitation by counter diffusion of cellulose. So sorry. Before this, I conducted some computational physics to estimate what concentration is actually needed. So what is the saturation index inside the chamber? And you can see here that we have the concentration profiles of strontium chloride and sodium sulfate. And then we can estimate that we have in the center region of our chamber a concentration of around 25 millimole per liter, which results in a saturation index of 2.2. So this should be high enough to trigger the precipitation. Coming to the results, I will present 2. The first one we can see here, so we have the porous reaction chamber here, and you can see how the pseudostine is growing, starting nucleating in the center region of the chamber, and then finally clogging the inlet. And what we could see later, just a couple of minutes, were that there was redissolution going on and enabling further precipitation reactions. In the second experiment, we could see that the nucleation and growth of cellulose actually started even, it was more in line with the expectation in the sense that it was even more in the center and symmetric part of the chamber. And again, the pseudostine is growing, clogging the chamber. And due to the inhibited mixing of the reactants, we can see dissolution and a kind of microporosity is forming and reprecipitation reactions. So just from the images, I could derive the crystal growth rates, and we could see due to the post-clogging reactions and further precipitation, we could see that the clogging had an impact on the precipitation rate. So it was lowering it down, and we could, of course, measure the critical porosity. So what is about the effective diffusivity in response to precipitation? For this, I conducted some pore-scale modeling studies. So using the 2-dimensional images, which were segmented in 3 phases. So the solid phase, pseudostine, aqueous phase. And then used as input for the first approach was the so-called trans-LBM. So that was a code provided from Yuan-Kai Yang, my colleague, and it's based on the Lattice-Boltzmann method. And here we can see that the effective diffusivity is decreasing with porosity. Another approach I was testing was the so-called MATLAB application tau factor, which yielded actually the same results, but which in the end was computationally more efficient. So I used this one for every single picture, every single time step I was capturing with the experiment. So we could see, or we could derive the diffusivity porosity relationship, but what was now with the critical effective porosity diffusivity at the crop state. For this, I conducted Raman isotopic tracer experiments. So as soon as the chamber was clogged, I injected the strontium chloride dissolved in pure deuterium. And what we can see here on the left side is the integrated intensity signal of the Raman modes representative for deuterium. And we can see how deuterium is diffusing into the chamber. Here we can see the intensity of the symmetric stretching mode of the sulfate. So that's the distribution of silistine. And after around 170 minutes, we can see that the intensity on the other side of the precipitation front is also increasing for deuterium, which shows us that there's still a diffusive process going on, and which allows us to estimate a critical effective diffusivity, which was in the end in the same order of magnitude as proposed by Deng et al. So trying to reproduce our experimental results by Archie's law showed that the experimental results were deviating towards clogging, and then testing the extended version of Archie's law proposed by Deng showed a significant improvement. Which brings me to the first conclusions I could draw on this little project. So we can say that Archie's law does not capture the evolution of the diffusivity in response to mineral precipitation reactions, and that an extended version improved the relationship or the description of it, but that post-clogging features are still not considered. So the still open question is what happens actually with the critical effective diffusivity if we think about, again, the redissolution and reprecipitation. So is there maybe a second state of clogging? And that with this, clogging represents a non-final state with a nonlinear feedback on the reaction kinetics. Just to give you a short insight into my second project that was more focused on the variations in the reactive regimes, so assessing the effect of the Dampkühler number on the porosity diffusivity relationship. For this, I used a slightly different setup, so it was also conducted with a microfluidic chip, which resembles a realistic pore geometry, and we injected, again, sodium sulfate and strontium chloride from one side at a very high flow rate to create such a sharp interface, so that we have diffusion across this interface from different initial concentrations. And what we could see here is that with increasing Dampkühler number, the distribution of silistine crystals was getting more and more non-uniform, and what was really special that we had, like, at such high concentration that the kinetically preferred silistine, the intermediate phase of silistine, was precipitating, incorporating water. So what we can see here is that just a slight increase in the reactivity of the system made Archie's law not applicable for the system to predict the effective diffusivity. The extended version was just, in this case, the extended version, I refer to the additional fitting parameter, was working out. But for the case of the intermediate phase precipitation, it was pretty tricky to find an equation or relationship that really captures this phenomenon, and still leaves behind a question mark regarding how long is this still actually this state present. So if we think about the redissolution of this intermediate and metastable phase and the reprecipitation of the water-free phase of silistine. And with this, I would like to thank you for your attention, and also again for my supervisors, Professor Dr. Dirk Bosbach and Dr. Janak Musami, and my colleagues during my PhD time.
Super. Thank you very much, Mara. So I welcome the audience to write the questions down in the comments so we can read it here. I have one in the meantime. So did you also mention that you observed the dissolution as well of the, is it of the solid of the PDMS? Does it attack the PDMS?
I don't suggest. So there were limitations regarding the PDMS glass chips because the PDMS is also altering at a specific time, and you can actually trace it, or I could see it because when you do permanent Raman mapping, so if you measure the whole area by Raman, and the PDMS detaches from the glass, gas will introduce or will come into your system, and gas is easy to measure. So I had, for example, so there were, of course, I did more than those 2 experiments, and some experiments failed because it was detaching from the glass, and then you couldn't see like really sharp lines from the gas. So it was limited in time, the total time of the experiment, but also good controlled by continuous Raman mapping.
But in the experience that you have shown, the pillars, are they always PDMS or is it glass?
So the pillars, so inside where it was growing, there was a solution, and the other one was just glass. So
So you had both types there?
Yeah.
Okay. And does the Celestine block the whole channel? Do you know if like the crystal grows the whole height, or is it possible for fluids to go above or under?
That's a good question. I wouldn't say so, because this is what I would also see in Raman, because water is a very good Raman scatterer. And if you can do also like a Z profiling. So if there would be water above or below the Celestine, I would have seen it. I'm pretty sure.
So most likely it's blocking the whole height of the channel.
Yeah. And for me, the final proof was actually the injection of deuterium, and to see, okay, or even that it's really redissolving just by looking at the images, it was visible. And I think that's only possible if you have an inhibited transport of the reactants, right? So that you have that you reach like an undersaturated state locally along the mineral fluid interfaces. And then that was really interesting in my point of view, the reprecipitation, where I asked myself, okay, is it taking the sulfate that was just redissolved or from the just coming in? You know what I mean?
Yeah, I see.
So, but it was not so easy to prepare, like, so the idea was to do labeled or to produce a labeled solution of sulfate with 18O to see, is this the 18O just redissolved or the new 18O I'm injecting? Yeah.
Do we have any more questions from the studio?
I have just a curiosity. In your first project, did you also try it with some heterogeneous geometries of the microfluidics, or just with these homogeneous distributions of the pillars?
Just with this one. That was also the idea, but yeah. I also tried this with the second setup, but it was taking too much time because it was the second chip was pretty big, and just from the modeling I could calculate, okay, it needs 14 days to expect precipitation because it takes so long to diffuse from one end to the other end. But in this case, it was a little bit tricky to provide a purely diffusive system. So that I think that's the one point you really need to take care if you're using the microfluidics, that you create a purely diffusive system, because it's very sensitive if you just, so. But that was actually also the idea, to do it with different pore sizes, pore geometries.
Thanks.
May I have just another quick question?
Yeah.
So, did you have any problems with leakage, with like the Celestine inducing any sort of stresses that could lead to leakage, or was this not a problem?
In the second setup, because it was just too high in concentration, of course, at a specific one. In the first, no, it was. Okay. It was just limited, because for me it would have been also interesting to leave the experiment just running it longer to see what is with the critical effective diffusivity happening. So, for example, we could have just changed the solution again back to a normal to see how now water is diffusing and where the deuterium is going, for example, or But the PDMS is also degrading after a while.
Right.
I would also have a question, just out of curiosity again. So you were mentioning like the microporosity forming due to precipitation and dissolution happening successively can affect your diffusivity. So do you have any insight how you can take this into account in your final effective diffusivity, or do you have any ideas of how to address that?
One idea is, or to think more applicated, is to do sensitivity analysis. And right now, this idea of getting critical diffusivity, I don't give it up in the sense of that I'm transferring this idea now to the glass corrosion topic.
Yeah. Okay.
So, and we have, for example, now a setup which is a little bit larger, which also allows us to do these Raman isotope trace experiments, and where we can estimate effective diffusivity as a function of the evolving porous medium. In this case, it's the thicker layer of the glass. So I'm trying to getting more experimental results. But for now, I would say that the sensitivity analysis would be one way to go. But yeah,
okay, yeah. I mean, that's good news. Like you're still investigating this in your current project. I like the idea. Thank you.
Thanks.
Super. So if there are no more questions, I think we can move on to our second speaker of the day. So we welcome Iman Kivi. Iman is a Mahikihi postdoctoral research fellow at the Department of Earth Sciences and Engineering, Imperial College London, the UK. He received his PhD in petroleum engineering from Tehran Polytechnic in Iran. His research focuses on understanding and quantifying coupled thermo-hydromechanical chemical processes in porous media to enable the safe and efficient deployment of low-carbon geoenergy technologies. And his talk today has a title, Simplified Physics Model for Regional Screening of Subsurface CO2 Storage Resources under Induced Seismicity Constraints. So, Iman, if you're ready, the floor is yours.
Okay, thank you, Marcel, for the introduction, and thank you all for joining. I would also like to thank other contributors to this work, Silvia De Simone from the Spanish National Research Council, and Sam Kerber from Imperial College. So yeah, my research focuses on coupled THMC processes in low carbon geoenergies, but what I want to discuss today is a little bit different. I want to talk about simplified physics models for screening subsurface CO2 storage resources constrained by the risk of induced seismicity. So first, to remind you of the scale of CCS, carbon capture and storage, that we need to mitigate the climate change crisis. So we definitely need a rapid and wide energy transition to cut CO2 emissions. But even if the energy market goes fully electrified tomorrow, there are still some industries like steel, chemicals, and cement industries that are going to emit CO2 into the atmosphere because of the processes that they involve that produce CO2. So we need carbon capture and storage to offset these emissions. And these hard-to-abate industries contribute to some 20 to 30% of total emissions each year, which counts to some 10 gigatons of CO2 annually. So based on these trends, if you take a look at the projections of different technologies to limit global warming, for example, this one on the right provided by the Intergovernmental Panel on Climate Change, some 80 pathways to limit warming to 1.5 degrees C and more than 100 to limit it to 2 degrees C. All these pathways rely on huge amounts of CO2 to be captured and stored deep underground, with rates reaching some 10 gigatons by the mid-century and even more than that in the second half of the century. And cumulatively, this means that we are going to inject several hundred gigatons of CO2 into the subsurface if we want to reach our climate goals. But this raises an important question. If there is enough storage resources in the subsurface to safely accommodate this large amount of CO2. One of the key challenges is induced seismicity. In recent years, different geoenergy applications has led to seismicity. They are usually of a small magnitude. We call them microseismicity, but sometimes they're large enough to be felt at the surface and cause concerns and problems. So you see here a compilation of seismic events triggered by low carbon geoenergies, geologic gas storage, hydraulic fracturing, geothermal activities, and wastewater disposal, with some featured examples provided here, the case of magnitude 3.4 in Basel and magnitude 5.4 in Pohang, South Korea. both triggered by enhanced geothermal system activities. The case of Castor in coast of Spain induced a magnitude 4.2 by underground gas storage at the very beginning of the storage. And also several cases of moderate size earthquake in central US by wastewater disposal. These events have negatively affected the public perception of these activities. In some cases, they led to immature termination of the projects and even caused damage to the infrastructure. In the case of CCS, the megaton scale projects that have been implemented so far just induce microseismic events. But there's still an open question whether with the scale up of CCS to the climate relevant scale, the seismic activity grows or not. In fact, at the gigaton scale, we have multiple injection sites, as you see here on the left, that are injecting simultaneously into the same aquifer. So they are going to affect a large spatial extent in the subsurface, which may cross with several faults. So we are going to affect the stability of this fault through pressurization of the aquifer. And we need to consider these when we are talking about CCS scale up. But how is the reservoir pressurization affecting fault stability? Suppose that we have a fault here on the right, as you see in the subsurface. The initial state of stress projects a shear stress on the fault and a normal stress clamping the fault. We can express the stability of the fault in terms of the column failure stress, that is a competition between shear stress that tends to initiate a slip on the fault, and also the frictional resistance, that is a function of the friction coefficient, and the effective normal stress, that is normal stress minus pore pressure. So any thermo, hydro, mechanical, chemical processes that change any of these parameters could change the stability of the fault. So it is explained here on the bottom right side. You see the initial state of stress in this black circle. When we inject, we are going to pressurize the subsurface. So we are reducing the normal effective stress. So we are shifting this more circle toward the left, toward failure envelope. And this pressurization is more pronounced at the gigaton scale compared to megaton scale that has been in place so far. Because we have multiple injection sites, so we are going to have the interference of the pressure fronts from each of these sites that could build up large pressure in the aquifer. But besides, we have other triggering mechanisms, for example, pore-elastic stresses that could affect both normal stress and shear stress. So they either enlarge or shrink the Mohr circle, in that they are increasing or decreasing the fault stability. The same story for thermal effects, because CO2 reaches the subsurface at a lower temperature. So it cools down the area around the wellbore. So it triggers some thermal stresses in the same way as pore-elastic. It changes the shear stress. So it may enlarge the Mohr circle and bring it the conditions more toward the critical conditions for sleeping. We have also chemical effects as CO2 dissolves in water, create some acidic environment in the subsurface, so triggering some chemical reactions, changing in the composition of the fault, which means change in the frictional properties of the fault. So if these perturbations are large enough to bring the fault to failure conditions, we can expect that some part of the stored elastic energy in the subsurface under certain conditions could be released as seismic waves. That is what is named induced seismicity. But how is this induced seismicity affect the use of subsurface CO2 storage resources? It's a tricky question and challenging, because if we want to deal with all these THMC processes triggering seismicity, we need to do numerical simulations. We need huge computational resources to deal with that. And at the regional scale of investigation, it may be impossible, and with large spatial and temporal scale of interest to the problem. And also, our knowledge of the subsurface at this regional scale implementation is limited. We don't know the exact location of the faults, their properties, geomechanical properties, stress conditions. So we have developed a tool named CO2 block size to deal with these challenges. it uses simplified physics models with some simplifying assumptions to test different possible injection scenarios based on the number of sites and the distances between them, to find how much CO2 we can inject into the subsurface while keeping the seismicity risk at a low level. The tool has two modules: a probabilistic module that deals with the uncertainties in geomechanical properties, fault attributes, a state of stress, pore pressure, and frictional properties of the fault. So it do a Monte Carlo simulation, and the final output is a curve something like this. It is a slip probability for each of the faults in the study area as a function of pore pressure. On the other hand, we have a hydrogeology model, again, based on simplified physics models, simplified two-phase flow, with simplified rock properties and reservoir geometry, using analytical solutions that calculates the distribution of pore pressure in the study area at regional scale for bounded or unbounded boundary reservoir conditions, and also for time varying injection rates, so that we can replicate different stages of the CO2 injection lifetime. So the output of this module is the pressure evolution versus time. So it is then straightforward to integrate the two modules. We have a slip probability as a function of pressure. We have pressure as a function of time. So we can easily calculate the evolution of a slip probability as a function of time. And this is exactly what we need to deal with the slip probability of the fault at different stages of CO2 injection. But beside the risk of induced seismicity, we have also dealt with the risk of caprock integrity issues caused by tensile fracturing of the caprock. But it's more straightforward to deal with that, because it is just based on, it is just a function of the pore pressure changes in the reservoir, which is provided by the hydrogeology model here, and also the fracturing limit of the caprock, which is a function of the minimum principal stress and pore pressure. And I will later, in an example, I will provide the details of these calculations. We have demonstrated the tool against induced seismicity at regional scale in Oklahoma, caused by wastewater disposal into the subsurface. But I just skipped this part because of the lack of time. But if you're interested, you can take a look at the paper for more details about that. What I want to discuss here is about the application of the tool for a storage resource assessment in Utsira Formation in the Norwegian sector of the North Sea. So you see the extent of the formation here on the left. It is extended in south-north direction. The contour shows the depth of the top of the formation. It is too shallow in the middle part, intermediate range in the southern part, and deeper in the northern part. We just focus on the southern because of proper reservoir properties, high porosity, high permeability, high thickness, and also the depth is quite okay, 900 meters more or less. And the lines here in black shows the mapped faults in the study area. So as I mentioned before, the tool tests different scenarios for injection with different number of injection size and distances between them, which are shown here in these small rectangles, different grids, possible grids, some examples of all tested grids in it. And you see the distribution of pore pressure after 50 years of injection with a constant injection rate per site of 10 megaton per year. So it is clear to observe that with increasing the number of injection sites, with reducing the distance between the injection sites, we have a larger pressure buildup because of the interference between pressure fronts of individual sites. So with this, we can skip to the other module, geomechanical module, and the parameterization of the statistical distribution of different parameters. We use a uniform distribution for pore pressure and assume a hydrostatic distribution and normal distribution for other parameters. We assume normal stress regime based on field measurements, and again, for other parameters, friction coefficient and fault attributes, strike and inclination, we consider normal distribution. For this normal stress regime, one of the main parameters contributing to fault stability is the inclination of the fault, which is usually less constrained compared to other parameters. So we just assume a normal distribution around 60 degrees, which is more or less the orientation, which is the faults are optimally oriented for sleeping, as kind of conservative assumption with our estimates of fault stability. So this is the output of this module. It is fault stability as a function of pore pressure for all faults mapped in the study area. And the colors shows the sleep probability after 50 years of injection. The curves all following an S shape. It means that at the beginning, with increase in pore pressure for 1 or 2 MPa, we have very small increase in the sleep probability, but with further pressurizing the reservoir, the sleep probability increases abruptly. So this is a very important trend that affects our estimates of fault stability evolution versus time. You see here the distribution of fault stability, fault sleep probability after 50 years of injection in the study area. And as we could expect it, these faults in the middle of the injection grid has higher sleep probability because of higher pore pressure buildup. But if you take a look at the trends, you see that different segments of the same fault, which are located at close vicinity, and pressure buildup are almost the same for these segments, they may have different sleep probabilities. And it is related to the direction, to the strike orientation of the fault segments relative to the maximum horizontal stress. Those at some angles with maximum horizontal stress experience larger increase in fault stability because it projects large shear stress on the fault, while those perpendicular to the horizontal stress, maximum horizontal stress, have low fault stability because it tends to increase the normal stress and keep the fault stable in the subsurface. And then with some simplifying assumptions, we could provide some estimates of possible seismic magnitude that could expect after sleeping on the critically stressed fault segments. The first assumption is that a sleeping occurs on the full length of the fault. It's kind of conservative assumption because usually fault rupture take place on small portions of the total length of the fault. And also the second assumption is that the stress drop equals 1 MPa after sleeping, which has shown to well reproduce induced seismicity events with within different geoenergy projects. So you see here for this particular distribution of the injection site, we can expect an earthquake magnitude of up to 4.6. This kind of map of distribution of potential seismic magnitudes provide a rough and preliminary seismic hazard and risk map, but if we need to provide a more accurate one, we need to overlay this map with the distribution of infrastructure, population, seismic velocities, and ground motion to have a better idea of seismic risk and hazard following CO2 injection. And as I mentioned, the other parameter that we have taken into account is caprock integrity. On the left, you see a schematic of the evolution of minimum horizontal stress and pore pressure. And the difference between the two is the fracturing limit. In fact, this is the maximum pressure increase that the caprock can sustain without tensile fracturing in the caprock. And you see that this is a direct function of the depth. So with the changes in topography of the reservoir, we can expect different fracturing limits. You see here the calculations of the distribution of the fracturing limit for the Otsiro formation that follows the same trends as the depth. Yeah, we have this part in the middle part, which was shallow and have kind of minimum fracturing pressure. In the southern part, we have intermediate fracturing pressure of some 5 to 6 MPa, and it is in the northern part that has the maximum fracturing pressure. On the other hand, we have pressure evolution for a particular grid of dense grid of injection sites, creating a distribution of pressure with maximum of 5 to 6, more or less comparable to that of fracturing pressure. So it's kind of critical injection scenario. If we subtract the fracturing pressure from from the pressure distribution, we can define an excess pressure term here, in which positive values in red shows places that we have probably exceeded the tensile fracturing of the caprock. So these are producing issues with caprock integrity. And these regions with negative values in blue are regions that are more safe to inject. And this set a useful parameter for make comparison between different injection scenarios. And you see here finally a comparison between the two constraints. On the left, induced seismicity, on the right, caprock integrity. Those values on the y-axis shows the number of injection sites. Those in the on the x-axis shows the distance between the injection sites. And the numbers within the cells shows the storage capacity. And the color on the left shows maximum slip probability of an earthquake with magnitude larger than 4, and on the right the color shows that excess pressure that I defined in the previous slide. So negative values means safe conditions, positive values means most likely we will have issues with caprock integrity. So you see that we can inject some 12 gigatons of CO2 into this southern region of Otsira formation while keeping the induced seismicity risk at a low level. On the other hand, we can inject some 18 gigatons of CO2 without having caprock integrity issues. So a simple comparison between the two clearly shows that induced seismicity is most likely the factor that is limiting injection in this site. The conclusion can vary from site to site because of the change in parameters, in particular change in the distribution of in situ stress. But I should note that the case of Otsira formation is a featured example because it's relatively shallow compared to other candidate sites for CO2 storage. And these kind of shallow reservoirs favor the conditions in which caprock integrity should be an issue. But even with these conditions, induced seismicity is recognized here as a limiting factor and should be considered when we are talking about CCS scale-up. And with that, I would like just to wrap up. So CO2 block size does not aim to provide a definitive assessment of injection-induced seismicity. If you're interested in such kind of accurate assessment of seismic risk and hazard, you need to do site-scale numerical simulations in which multi-physics issues of the problem and also complexities of a structure in the subsurface can be reflected in these models. More physical complexities can be embedded into the tool. In particular, pore-elastic stresses can be calculated using analytical solutions under anisotropic conditions and with heterogeneity. So this can be our next addition to the tool. CO2 block size can be combined with monitoring techniques for improved reservoir characterization. Indeed, at such regional scale, our knowledge of the subsurface is limited at the beginning. So we need to learn as we inject. And for that, we need to use physics-based models to interpret the monitored data during the operation. And these kind of analytical models can provide a foundation for this integration. Storage resources can be expanded with optimized well placement. Indeed, what we have now is a regular distribution of the injection sites on rectangular grids, but with proper optimization of the site locations, we may open up some more room for CO2 injection. And we need to consider the distribution of population, infrastructure, and how the surface could be affected by moderate-sized earthquakes. And finally, the use of induced seismicity as a limiting factor may enable more restrictive estimates of the CCS scale-up rates at regional and global scales. And with that, thank you all for your attention, and I would be happy to answer any questions if you have any.
Great talk, Iman. Really, it was super interesting. So I'm inviting anybody with questions from the audience to just drop comments in the YouTube, and we will read them out loud. And in the meantime, I will start with a couple of questions of my own. So I'm not really an expert of this topic, so sorry if I'm wrong, but I saw that you have a bunch of parameters in your model, in your approach. And these parameters are like the geomechanical properties, right, of your system. So I was wondering, are these parameters somehow like cross-correlated or just autocorrelated in space, or if you can comment on that in general, and how you account for that correlation in case?
Yeah, okay, great question. Yeah, indeed, for this example, I just used a single distribution of parameters for the whole study area, but this capability is provided in the tool if you have a large region in which, for example, the state of stress could vary from one side to the other. You can assign different distribution to different regions. So you can have different distributions reflecting the spatial distribution of these parameters across the study area.
Cool. Yeah, that's super nice. Thanks. And again, along the same line, more or less. So you assign this like Gaussian distribution to some of these parameters and a uniform distribution to another one. So I was wondering, I mean, do you start with this assumption for some specific reason? I mean, do you have some evidence from some data of these kind of distributions, or I don't know?
Yeah, this is in fact a starting point of the distribution of the parameters, but usually, in fact, it is based on the data from the literature, how these parameters are distributed at regional scale. So this kind of distribution, for example, uniform, the most simple kind of distribution of parameters could reflect the pore pressure in this region, kind of more uniform distribution, while the Gaussian distribution, normal distribution, have been found to well reproduce the other parameters in the literature. So they are based on some insights from the distribution of the spatial distribution of these parameters in different regions around the world from the literature, but you can assign any other distribution that you like.
Okay.
Yeah,
Do you have other questions from the studio?
Yeah, just following up on that. So is this kind of distribution set up for a specific type of rocks, or do you consider different type of rocks within a single distribution? How do you deal with that? Are you assuming that you would have one type of rock in a specific region or an area and then distribute different distribution?
Yeah, it depends on the distribution of the parameters in the study area. In fact, if it is kind of uniform in the study area, you can assign just one distribution. But for example, in the case of Oklahoma, as I mentioned before, that is the demonstration study that we carried out for the tool, we have large changes in the state of stress from one region to the other, from south to north of Oklahoma. So we need to assign different distributions for example, the state of stress, or for example, the frictional properties of the rock, depending on the rock geology, can change significantly. But yeah, it's the most simple scenario to have one distribution, but you can assign different distributions depending on the rock properties, on the distribution of the state of stress in the study area.
Great, awesome. And I will have again another question. By the way, it was a really interesting talk. I enjoyed it so much. So currently you're just considering the uncertainties on your main parameters, which are your geochemical one. But you mentioned that you still have simplified models assumptions. So are you thinking about copying everything and quantify the uncertainties on your analytical model as well? Or do you want to keep like the Monte Carlo approach for the parameters and maybe leverage more high level simulations?
Yeah. Okay. So
after all?
yeah, the primary goal of this study is for very rough, very rapid, and first-order screening of subsurface CO2 storage resources constrained by induced seismicity. But it's a real challenging problem to deal with induced seismicity. It is a function of different multi-physics processes. And
Yeah.
if you like to deal with all these challenges, you cannot use this kind of simplified analytical solutions.
No, you're sure?
Yeah, if you want to deal with more accurate seismicity risk and hazard assessment, then you need to do numerical simulations with high fidelity numerical simulations at site scale with all these complexities of the topography of the subsurface, complexities related to faults, if the faults are permeable or impermeable. So these complexities should all be incorporated into your models.
Yeah, yeah, right. So for instance, what I have in mind is like multi-level Monte Carlo approach, for instance, coupling high fidelity models with low fidelity analytical tools. So do you see something like that as a prospect for your work or not at all?
Yeah, I think so. For example, having analytical solutions for larger scale, and then the output of these analysis can be used for example, for boundary conditions or initial conditions for tuning site scale numerical simulations. Yeah, it is doable, but at the moment, because our perspective is to apply these tools to different regions around the world so that we can get a more kind of reliable insights into how much CO2 we can inject globally into the subsurface in the coming decades.
Yeah, great. Thank you. Thank you very much, Iman.
I have just one quick question. So it's I think one of the nice things that you can get out of this model is that you can also see what kind of parameters are more relevant and how the uncertainty in these parameters are more relevant for your prediction at the end. Let's say if you have this many sites and at this distance, that's your maximum at a safe situation, right?
Yeah.
So you showed this distribution of the different geomechanical parameters there with different standard deviations. Could you access measuring all of these things cost money, right? And people don't know sometimes in advance what if you have this much money that you can put into measure it, how to distribute it, what is the parameter that you want to know with the highest certainty, because that matters the most for your prediction at the end. Could this kind of modeling help to answer these questions?
Yeah, so in the paper accompanying this work, we have provided a tornado graph, for example, to provide some insights on the importance of each of these parameters when dealing with the risk of induced seismicity. So definitely a state of stress is the most important one, I would say. But when we are talking about regional scale implementation, it is not always possible to capture all these parameters, their distribution at such large spatial scale. Yeah. Finally, what we need to do is to learn during the operation. So we need kind of real-time monitoring, real-time characterization of the subsurface. So yeah, I would say we can limit the uncertainties at the beginning before injection. But finally, we need to add more information, update these distributions at the start injection. And this highlights the fully dynamic nature of the storage resources. We need to update the storage resources as we learn about the subsurface and update the perspective of CCS technology.
Super, thanks.
Great. So there is a comment from Idris that is just congratulating for the talk. Great talk. Okay, so I guess that if we have no more questions from the audience or from the studio, we can close here with today's session. So before closing, I just want to thank our speaker and to thank my colleagues here in the studio, so Marcel and Sarah, for joining me. And I just want to advertise our next session, which is scheduled for the 19th of August. And we will have two great speakers. We will have Tracy Amaka Chukwuma from the University of Georgia and Leonardo Sandoval from the University of Arizona. So, well, that's all for us for today, and see you at our next session. Bye. Bye-bye.